make my background blurry, but I'm not sure now.
So I think we can start, Essam.
Sure. Okay. So, hello everyone. Welcome to another event from Montreal NLP Consortium. This event is the topic of this event is on question answering systems, and we have an interesting lineup of speakers joining us from Ukraine and from the west coast of the US. And yeah, so without further ado, I'm going to ask Dr. Jianyuni to do his opening remarks.
Okay, thank you, Hassan. It is my pleasure to chair this session of Meetup. It is a pleasure to have three speakers for this morning, and we will talk about the different aspects of question answering and also knowledge graph. This will be the last talk, and the speakers are from different places from the world. So we have time differences. So the sequence of presentation is made to accommodate the time difference, and we will start with Svitlana, Vakulenko, and then followed by Jianfeng Gao, and then by Filipe. And you will see that we will cover three different topics in this session. And I don't need to mention that question answering is an important topic in NLP, and this is really very useful kind of application in NLP, and it is involved in a lot of applications. Even in conversation, we may have the needs of question answering. So this is really an active research area, and we will see what's the recent progress in this area and what are the aspects on which people are working on. So I will not make a long introduction, and I will just introduce our first speaker, Svitlana Vakulenko, who is a postdoc now at the University of Amsterdam, and she got a PhD from Vienna University of Technology, and she also did an internship in Apple, and her main research topic is on QA and the conversation search. So this is really strongly related to question answering. And the topic of her top talk today is about question rewriting in QA. So I give the speech to Svitlana, please.
Thank you, Dr. Ni. I'm sorry, just before we proceed to this start. So I would really appreciate it if all the participants turn on their microphones and cameras during the presentation in order to keep the focus on the speaker and have a better experience with the event. So yeah, I'm going to start with myself. So Svitlana, the floor is yours.
Thank you for the introduction. Let me share my screen quickly. Okay, can you see it? No. I think. Maybe. Can you tell me whether you can see, because maybe you're muted?
We can see a paper.
Okay, wrong one. Stop. Let's try again. Maybe now?
No, not now.
At the very beginning, I think we could see it.
Okay. For some reason it doesn't show. Now it should work, right?
Yes.
Yes.
Thank you.
Just enter. Now it should be full screen, correct?
Yes.
Yes.
Perfect. All right. I'm going to present our recent work using question rewriting for the task of conversational question answering. Let me dive right in. So the task in conversational question answering is to answer a sequence of questions where each follow-up question may depend on the conversational context. So the previous turns either question or an answer. So in this example, we see two phenomena that are frequently observed in conversational question answering, which are anaphoric expressions and ellipses. So in cases of anaphora, we usually have pronouns that would refer to entities or nouns mentioned previously. In case of ellipses, makes it even harder because there are some tokens missing from the question that are required to unambiguously interpret it. The way we propose to approach this task is by resolving this ambiguity, rewriting the questions into their unambiguous equivalents that would result in the correct answer, but outside of the conversation context as well. So we would replace pronouns, anaphoras, with their respective coreferences and insert the missing tokens from the previous conversation terms. Essentially, what it gives us that we introduce two subtasks. In the first part, we translate from potentially implicit or incomplete question conditioned on the conversation context into explicit question, which can be answered using traditional question answering models. Which makes sense for several reasons. So in the first place, it's reuse, but also certain transparency in the understanding whether the errors come from the interpreting the context of the conversation or answering the question. There are several approaches I'm going to introduce here, and the first one can be described as a simple unsupervised approach that can reuse existing coreference resolution approaches. So there can be models that are already trained on this task that we can just apply in this context. So it's more difficult to resolve ellipses, but there are also there's some work done using heuristic, basically rule-based approaches that would detect topics as nouns and then topic shifts using some lexical cues. The approach we were working on is sequence to sequence, when we use a corpus of conversational questions with paired with their unambiguous rewrites, and then we can train a model end-to-end, basically from inputting context of a conversation with the question towards rewriting into an explicit question. So we used a pre-trained transformer model and just fine-tune it on this task using a big corpus of conversational questions. So one thing we noticed in this approach that is important that the model we use has a big capacity because it's a difficult task. So the bigger the model, we see always improvement in the performance. So at the time when we were running these experiments a year ago, the biggest model was GPT-2. So we found one approach that worked well to improve capacity of this model by adding another layer. So it's similar to pointer generator approach when we have two distributions, one copy and another one that would be generating. And here we found that actually two generative heads work even better. So we learn to produce two distributions using the last hidden state of the transformer, and then also you learn the parameters to linearly combine the predictions of these two heads. One approach which was inspired by the same idea, same type of model, it was presented in CLIQ-ai this year. The difference here, they use rule-based and self-learning approach to constructing conversations. So they are not operating on the kind of supervised corpus we had access to, but instead they were using MS Marco sessions where the questions are unambiguous, but in order to simulate the conversational scenario with this implicit questions, they would apply either rule-based approach or self-learning approach, so pre-trained on a small set of conversations. So the benefit, essentially it combines the previous two approaches I described, rule-based with sequence to sequence. The benefit here is that by generating these training examples automatically, we can control for the number. So we can modify the distribution over sample hard cases using this rule-based. For example, ellipses occur less often naturally, but this approach can help to generate more samples. A more original approach to the same task was presented also in CLIQ-ai. And the difference here is that instead of predicting sequence to sequence, the goal is to sample the tokens from the conversation history, which are required to disambiguate the conversational question. So it's formulated as a token sequence binary term classification. So for each of the tokens, so here I just assume that the words are the tokens. For each token in the conversation history, we either generate 0 or 1. So 1 would indicate the tokens that we want to use to expand the context, and they will be just appended to the original question. So this model was also trained on the same dataset we used, and the advantage here, since it's not a generative model, we can actually use encoder models, so transformers with bidirectional attention, which are more powerful than the generative ones. All right, so in the paper that we will be presenting next year, actually, we show that the approach we took with sequence-to-sequence modeling outperformed the other approaches, related approaches presented in the previous work. Moreover, we also compare it with a set of baselines. So we use a similar baseline using original, so previous terms with tokens selected by IDF heuristics. And then we have a few baselines, different transformer architecture and coreference baseline. So we see an improvement in performance in comparison with the original questions, and it gets quite close to the human written questions. Moreover, we also, in this paper, we present experiments not only on the TrackCast dataset that was used by models I was presenting before. So in TrackCast, the task is conversational passage ranking. So the answer there has to be retrieved from a collection of million passages. Canner dataset was originally created to augment questions in CLIQ, which is a dataset for conversational reading comprehension. So there the task is to extract a text band from given a text document. And in this paper we show that this question writing approach works equally well, not equally, but it improves performance for both of the tasks. And we also used the same model. So since TrackCast is a small data set, it just has 80 dialects. We actually trained a single question writing model and applied it to both of the data set at inference time for evaluation. So these are the results on Canard and CLIQ dataset. And we see similar results, so that the best transformer model we used improves the performance, and it gets closer to human rewrites. but the difference is smaller in comparison to the regional questions. So one other thing I wanted to mention about this setup in general is that by introducing the subtask of question rewriting, we are also able to better understand the performance of the model. As I mentioned earlier, the errors can occur either at question formulation time, so that the question, the way the model understands the conversation and generates a question might not reflect, so prevents it from discovering the correct answer. And otherwise, the question might be correct, but if question answering component fails, that we are not able to discover the answer. So the intuition here that we want to understand for each of the cases, each of the samples in our dataset, what is the source of error. And there is one elegant way to do it automatically. So since for each sample we have 3 types of rewrites. The first one is the original question in the conversation. The second is the one produced by our model, and the third one is the ground truth produced by humans. So each of these questions can be used in the question answering model to measure, to compare the generated produced answer with the ground truth answer. So we get a score, and then each of the samples we can cluster. So according to this matrix, we can define a threshold. So NDCG at 3 is a ranking matrix. We can design a threshold of, let's say, 0.9 we can consider as correct, and then calculate for each of these clusters how many samples fall into each of these groups. So this gives us our results in a nice interpretable manner. So what it shows now here is for TrackCast 2019. We show the percentage of errors that stem from incorrect question answering. So this is the blue area here. It shows us that even for human rewrites, we are not able to discover a correct answer. So this means we cannot really judge about quality of question rewriting using basically answers from question answering. So here the orange and the green parts, they show either correct samples, so when the human rewrites result in the correct answer, then if the generated rewrites are not producing correct answer, that we know that this is the error, the error is on the part of question rewriting model, or if the question rewriting model works in this case. So the other 2 cases is when even the original, so all of the formulations result in the correct answer, which means there is no rewriting required. So even if the model changes the question, it doesn't affect the performance. So this is the area that shows us basically false positive and true positive in the cases where rewriting is not needed. There is an interesting also anomalies that can be observed in this case. For example, is called superhuman resolution, when question rewriting models actually performs better than human rewrites. So the interesting observation we make using these 2 models is that they perform drastically different. So we can compare passage ranking models with reading comprehension. The difference here is that in reading comprehension, rewriting is actually not as critical as in passage ranking, meaning that even incomplete questions would still get the correct answer in this case. So we also can observe it by looking at the difference between questions and answers. So here we would measure the difference between 2 questions as using Rouge and the produced answers using set overlap. And in passage ranking, it's not possible that very similar questions would result in the correct answer. So this is impossible. And here we see in reading comprehension, we see less correlation. So I have a few examples here just to illustrate it a little bit what I mean. So this is an example where very similar questions, they result in different answers. So it might be just one token difference, but the ranking is drastically different. And the other way around. So it might be that the question is very different, so the paraphrase, but then it results in exactly the same answer. So this just shows that if we evaluate question writing independently from the quality of question answering, it's not necessarily, it doesn't necessarily show us that the performance on the end-to-end task. And the bottom table shows the results from reading comprehension. Here we observe that even so lowercase changes the results. So here the difference between two questions is really just the title is lowercased by the model because it just doesn't predict cases. And the answer by reading comprehension model is just completely different. So it's quite brittle training. And here is opposite. So we have a completely implicit question that without rewriting, without the resolution, it produces a correct answer. So the TrackCast challenge continued this year. So we just had the presentation last week. And I think I'm not really entitled to discuss the results, but there is a new data set this year, and it will continue also next year. So it changes slightly over time. What we observe in the new data set on conversational assistance track is that the samples, the distribution of samples changed quite a bit. So here you can observe that originally most of the question actually does not require, so they can be solved without rewriting using implicit questions, and there are quite so much less samples like this in the second year of TrackCast. So we also see that the best models we had are changed. So now accurate text, so this binary classification approach works better. We also see that there are more errors, it produces more errors, but in this case it performs better because it's targeted towards hard cases where context tokens have to be sampled. So the transformer model was more traditionally, so more conservative towards so copying the original question. Another change this year was that some of the questions were conditioned on the answers. So it's just to illustrate that it's difficult because it's conversational passage ranking. The answer here is the whole passage. So this actually breaks quite some of the models just because the length of the answer doesn't fit. So in this case, the model works, but I think it's also a simpler case because the correct answer that has to be used for rewriting is the first two tokens. So this might be the reason why it worked. All right, so these are the papers I used in this presentation. And there are 3 more submissions that we are about, that are currently under review, so including the notebook for track this year. And I would like to mention the team I was working with, Shane and Mikael. I met in Apple last summer when I started working on this project. Ravi was my mentor, and with Nikos we collaborated on this year's submission. And to conclude, I just want to give you this metaphor about the framework of question writing. So you can think about it as this power adapter. So if I would come to present this work in Montreal, I wouldn't need to buy a new hair dryer, but I can just adapt to the new context using this extra element that instead of retraining the whole question answering model, we can just retrain the component that would be formulating the questions conditioned on the context. So this can be also applied to different setups. So here we showed results on conversational context rewriting where the question generation was conditioned on the conversation history. There could be other examples. So we can condition generation on the user profile or on some environment variables. So this approach is more of a framework that can allow to use different question answering models as long as we can translate from the context towards a standalone question. So this approach is modular, allows us to reuse existing models. Also, as I showed, it allows us to get an insights about the functioning, robustness of these models. It also helps because the annotating question to answer mapping, it might be more expensive than annotating the translation part. So how to convert from the conversational context to a standalone question. Last but not least, this is also useful in distributed environment. So if you want to target external APIs, we cannot just train end-to-end models. So this approach, if we generate independent questions, then we can also use them as input to different question answering models, assuming the input is a natural language text. This is the assumption we use. I'm not sure how well I'm on time. Yeah, quite.
You have 2 more minutes for the presentation.
I think I'm done with slides. If you have any questions.
So thank you very much for a very interesting presentation.
Thank you. So that now is a period of questions. So I don't know how it's going to work.
Yep.
Can
so
someone just,
yeah, sure. So for the question period, what we're suggesting the audience to do is to use the raise hand button in the panel below the screen. So using that, they can raise their hand and I will let them know when they can turn on their microphone and we can ask the questions. So we now have 10 minutes for the question answering period. So if someone has a question.
Yeah, I see Guy raise hand.
Yeah, sure. Dr. Lapin.
Yeah.
Okay, so thank you very much for this interesting presentation. I think you have a very clever approach. I was curious to know what size of context do you take into account, because a conversation usually has the context increases as the conversation goes on. It was not clear in your presentation if you only took the preceding question or the whole conversation. What is a conversation in your case?
Yeah, so the conversation is a sequence of question answer, and it depends, the statistics depends on the data set. So the data sets we used here in TrackCast is 5-6 turns. So this fit into the model, and we trained using the whole context. Empirically, we observed that it's sufficient to use the previous 2-3 turns. So it's less likely that the conversation will depend on longer conversation context. So the bottleneck appears when in conversational passage ranking. So as I showed you, the answer as a passage is quite long, so we can't really condition on all the answers, all the previous answers. So in this case, we use only a single previous answer, but all previous questions.
Okay, thank you.
Right. Any other questions? Or maybe
Yang.
Yeah, Zhao Liang. Yeah, Matt.
You can turn on your microphone. Yeah.
Okay, thank you for your talk. And I have a question. So I find that you use BERT to train the conversation context. But as the context grows longer, it might exceed the token number limit of BERT. So, like, I think BERT has a token number limit of like 512. What if you have more tokens given the growing context? What is your strategy?
Yeah, so far we could fit the whole conversation. So assuming this restriction that I mentioned before, clearly there is a limit. So the questions are relatively short. The answers can be long. So in case when we use passages, this is definitely a bottleneck. So I saw other teams that are using heuristics to sample tokens so basically to reduce length of the answers. So this could be one approach. If we look at real conversations, I mean, more like conversational answers, they tend to be short. So, and then it's possible to usually fit in the previous 2-3 turns. And then, yeah, there's obviously always could be a long tail of examples where there is longer dependency. But in the majority of cases, it looks like it's enough and it's sufficient to fit in the model.
Okay, thank you.
Good. So other questions?
I can ask a question, Svitlana. You mentioned a little bit about passage ranking and then text comprehension. Is there a difference between them for question rewriting? I mean, in passage ranking, it is also needed to expand your query to just search for relevant passages. And here the requirement for passage ranking in terms of question rewriting could be different from the second part, the text comprehension. Have you considered two different approaches for the two steps? Because they use the same rewriting process, right?
Right, so this is a good question. So in this work, in the process we do, we actually don't backpropagate from the retrieval step. So we assume we always target the correct question. So we assume there is a good question that can be asked independent of the question answering component. I agree there is a way to fine-tune also this question rewriting, question resolution approaches that can be fine-tuned end-to-end based on the answer we retrieve. But so this has a downside that it will work for one particular model. So the approaches we used so far, they assume they target the question, the correct question, not the correct answer. But so another part of the question is that efficient approaches for passage ranking, they often rely on bag-of-words models. So I think this might also explain why the binary classification model worked well, because it expanded, so it's efficient in terms of recall. So it oversamples the tokens, which allows us to recall more passages at the first stage before re-ranking. And then re-ranking approaches, they might be so more susceptible of noise in the question, so like malformed questions. So they would assume some word order. So there might be some interaction with this case, but yeah, in these experiments we actually assumed there is some so gold standard for the question independent of the question answering model. So it's a bit of a paradigm way to work with this problem.
I I think it works well for the collection you work on, and well, there could be some other situation in the application where you will need to consider both the steps or try to use end-to-end training for that. But this is another aspect that is not necessarily involved in the tracker collection.
Yeah, the problem with the end-to-end training is that we need it would improve on particular collection and particular model.
Mm-hmm.
So if
Yes.
this is a use case for a distributed system, an API that would query independently several collections, like you need to fine-tune for each model independently.
Yeah.
So I can see a question by Reza. Reza has a question. So Reza.
Yeah, I have two questions effectively. So there are two modules in this system. One of them is a question reformulation. The other one is the question answering module, right? So I'm wondering if there is a checkpoint there to see actually the question that is generated by the question reformulation is up to human standards, or whether it is what the second module likes to have. So maybe the second module is fine with not following grammar as long as you give that series of words to it, and it would still generate the correct answer. Did you do any kind of check to make sure that like the question generated, it's actually a question generated with proper grammar and proper way that a human would ask?
Yes, that relates to the previous question, I think. It depends on the objective. So one objective would be as we did. So the way we did it here is trying to generate the kind of question that the human would generate. So readable and interpretable by humans. The other approach would be to fine-tune it towards the question answering. So whatever question answering model helps it to retrieve the correct answers. So the problem with this approach is also that we might overfit. So we observe the cases where we would sample tokens that help to expand the topic. So they would co-occur with the topic in the answer passages, but they wouldn't actually mean anything. So you can't interpret this as a question. So it's more likely for classification, for binary classification model. For this sequence-to-sequence models, they tend to generate actually more human-like questions.
For the sequence-to-sequence version, there is no way to like enforce this, or you're just relying on the model? I'm just wondering.
Yeah, so basically this is a teacher forcing approach. So you force it to generate the kind of sequences that the humans have as a ground truth.
All right, thank you.
So we finished with the period of the question answering. Thank you very much again, Svitlana, for your great presentation, and the audience for the questions. So we are moving forward with the second speaker joining us from, I suppose, the Washington State in the West Coast. Jianfeng Gao is a distinguished scientist at Microsoft Research and the partner research manager of deep learning group at Microsoft Research. And his presentation topic is on a review on neural approaches to conversational question answering. So welcome, Jianfeng. The floor is yours.
Yeah, and let me share my screen. Okay, you see it?
Yes. Perfect. Thank you.
Okay, great. Yeah, thanks for inviting me to this interesting meeting. In this talk, I will present some of our recent works on neural approach to conversational question answering. Okay, good. Yeah, then the first question is that what is conversational question answering? A short answer is a conversational question answering system is a question answering system with a conversational interface through which a user can interact with the system to seek information via a multi-turn conversation of natural language. And if you have worked on task-oriented dialogue system, sometimes we call this task-oriented bot, you may notice that conversational question answering is an instance of task-oriented dialogue. So let's first review task-oriented dialogue system. A typical task-oriented dialogue system uses a modular architecture, which consists of mainly 4 modules. First is the so-called natural language understanding module that identifies the user intents and extracts associated slots and values from the user input, like this one. Like this one. Then the second module is called dialogue state tracking. Dialogue state tracking module that infers the dialogue brief state and converts dialogue into some formal queries to query the database for the answer and updates the dialogue state. The knowledge could be stored either in database or as a collection of documents. Then a dialogue policy module is used to select the next system action based on the dialogue state. And finally, a natural language generation module is used to convert the selected system action to a natural language responses that can be comprehensible by human users. Here is a dialogue of completing a multi-domain question answering task produced by a Microsoft Research System. You can see the user starts the conversation by asking for a recommendation of a museum in the center of town. And the system identifies user's request and provides a recommendation based on the search results from an attraction database. Here is the returned results from the attraction database. Here is the brief state based on which the system forms a query. And then we can see that through the conversation, the system develops the brief state, as I show here, the brief state, which can be viewed as the system's understanding of users' information needs and what's available in the database. Based on the brief state, then the system will pick the next action, either asking for more clarification or providing the user with the answer. And the example also presents some challenges in conversational question answering. For example, the system needs to understand the same area mentioned here refers to the center of town. This is the so-called co-reference resolution problem. Okay, I think the first speaker actually mentioned how to do query writing to resolve these problems. That's a very effective approach. In workflows, I will present a different approach. And depending on how knowledge is organized and stored, the conversational question answering system can be grouped into 2 big categories, what we call conversational question answering over knowledge base or text. In the former, the knowledge is organized using either a database or a knowledge graph. In the latter, the knowledge is represented by a collection of documents, like web collection. And a typical architecture of conversational knowledge base question answering system is composed of the following components, which is very, very similar to the modular architecture of task-oriented dialogue systems. First of all, we use a so-called semantic parser to map user query and the context to a meaning representation in formal language, which can be executed on the knowledge base to produce the answer. Then a dialog manager updates the dialog state to maintain the information, such as the entities, predicates, and the actions taken by the system or issued by the user from the dialog history, then select the next system action. And finally, a response generation module converts the system action to a natural language response. In what follows, I will describe each of these modules in detail, illustrated using examples. First, what is semantic parsing? Given question, user input question, its dialog history, and a table, for example. Like the one here, the parser needs to generate a formal query, which in this example is a SQL query that consists of a select statement and a 0 or more conditions. And the select statement is associated with a column name in the table, which is referred to as the answer column. And the conditions enforce additional constraints on which cell in the answer column can be chosen. For example, given a natural language query, which superheroes came from Earth and first appeared after 2009, the expected parsing results is a SQL query like select character where the home world is Earth and first appears larger than 2009. And the answer retrieved from database is Dragon Wing and Harmonia. Now, in a paper published in 2018, we formulated the parsing problem as a state action search problem, where a state is a complete or partial parse, which is an action sequence, and an action is an operation to extend a parse. And the parsing search and the parsing procedure actually searches an end state with the highest score. Actually, the table on the right, this table on the right, shows the type of actions and the number of action instances in each type, given an input natural language query. As I mentioned earlier, this query. Actually, one action sequence that represents the parse consists of 5 actions. Action 1, we need to select a column called character, then select a condition column called home world, then an operate, equal operate like Earth, then another conditional column called first appeared, then an operator great than 2009. I noticed that many states represent semantically equivalent parse. So to prove the search space, we define for each state the actions that can be taken, as shown in this figure. For example, start with state 0. We can take action. We always take action 1, which is to select a column. Then after we select column, we can take other actions like action 2 to select a condition column, then select an operator, then do it iteratively until we pass the whole input sentence. So we use beam search actually to find an end state with the highest score for inference. And the score can be computed recursively using the policy function pi here, which scores an action given the current state. The function is parameterized using different neural networks, each for one type of action type. For example, if we use the function called select action, the function is actually implemented using a DSSM-like model, which compare the semantic similarity between the words in the column name and the words in the question. And we can see that for different questions, the model will ensemble on the fly different neural networks that can be trained and trained. So in order to handle the follow-up questions in a conversational question answering session, we can extend the semantic parsing language by adding a preamble statement subsequent, as shown here. Subsequent statement contains only conditions, as it essentially adds constraints to the semantic parse of the previous question. For instance, if the follow-up question is here, which of them breathes fire? Then 2 more actions are added to extend the parse. One is add a condition column power, then add a equal operation, fire breeze. Then the here and the semantic parser is here. It's here. The corresponding parser is the subsequent where powers equal to 5 rays, and the answer is dragon wing, which is a subset of the previous answer. Now, recently there is a trend of using large-scale pre-trained language models for semantic parsing. Notice that semantic parsing requires to link the entity mentions and the predicates in a user utterance to the entities and the relations or column names in a database, respectively. This linking task is very challenging due to the diversity of natural language. For example, the same concepts can be expressed using different expressions in user questions and the knowledge base. And the linking task can be handled using neural networks that maps the natural language expressions into vectors in a hidden dimensional space, hidden high dimensional space, where the expressions with similar semantics are close to each other. And this year we developed a new model called SCORE, which is a pre-trained language model developed particularly for conversational knowledge-based question answering. This model is initialized using Robota and is then continuously pre-trained on labeled conversational semantic parsing database. As shown in this figure, the top part of this figure, a training example consists of user question, its dialog history, database schema, and target formal language. To train the model, we first need to concatenate user question, dialog history, and database schema as a long sequence. Then we feed that into a transformer encoder. The model is trained with respect to 3 different tasks. MLM stands for mask language modeling, which is a standard task training task used for BERT. And the other 2 tasks are designed specifically for conversational question answering. CCS stands for column context semantics. This task is intended to capture the alignment between user question and the formal queries, such as the predicates used in the user input and the column names in the formal language. The TSC stands for turn contextual switch. It's intended to capture how a formal query is changed with the conversational flow. As I mentioned in the previous example, when user ask follow-up questions, very likely the query, the formal language query, needs to be updated by adding conditional column and operations to reflect the user input. Okay. Actually, given this model, we can improve the previous semantic parsing algorithm very significantly. And the dialogue, the next module is the dialogue manager. And dialogue manager contains a policy for next action selection. In conversational question answering, actually the system's selection action could be either return the answer or ask clarification questions. Here I use a movie on demand domain as an example to illustrate how the dialogue policy works. Let's think about if the user asks a question like, the question is, okay, I need find me Bill Murray's movie, all right, but without any other conditions. The bot found in the database a lot of movies related to Bill Murray. So the system needs to ask some clarification questions to help narrow down the search space. Then the question is, what question to ask first? Then what clarifications to ask? We have different dialogue policies. The baseline policy is we can randomly pick a question. Then we can see that the performance is like this. The more question you asked, if you get the answer, more likely you're going to identify the correct answer. But we can do it better. Let's say if we always ask questions first, that these questions can be easily answered by the user. We can learn this information from query logs. So this actually improved the system effectiveness very significantly. Or we can take a different approach. We always ask the question that can narrow down the search space the most first. So this is called the entropy minimization-based policy. Okay? This requires you to understand the structure of the database. But we can do even better. We can ask questions that can complete the task successfully. This can be learned using deep reinforcement learning by aging user interactions. We can see from example that a good policy is very important for the effectiveness of a conversational question answering system. The last module is response generation. Let's say if the system pick a particular action item, the action needs to be converted into a natural language so that the user can understand it. And although traditionally this is implemented using template-based methods, these days neural approach became very popular. We can formulate natural language generation as a sequence-to-sequence task, where natural language model is trained on a future learning setting. That is, for each task, there's only very limited amount of training samples. And the state-of-the-art model we developed recently is called semantically constrained GPT. We published the paper, I think, recently. And for each task, actually, we need to feed in the model the dialogue X, which is specifying what to say. And then we also put the system response, the natural response as the target. So this specifies how the system say this response. Okay. The model is based on GPT. Now let's shift to another type, the other type of conversational question answering, which is based on a collection of documents. This is called conversational text question answering system. The architecture is very similar to conversational knowledge-based question answering system. And the main difference is that the semantic parser is replaced with a machine reading comprehension module. And unfortunately, we found that in the current market, there's not many very good data sets for this. So this is a very interesting analysis of two of the most popular data sets in the field. It seems that we still need a more comprehensive database to reflect all the compositional characters of the database. The state-of-the-art model Actually, there are two types of machine reading comprehension models. One is called abstractive, the other called extractive. I made a typo. This should be the extractive question answering, meaning that the answer is always a text span in the text, and we can we can formulate such problem as a classification problem. That is, we classify each word in the passage as a start, end, or outside of the answer span. And the most important components of this model is the encoding model, which represents each passage word using an integrated contextual vector that encodes the information about the word embedding, the passage context, the question context, and in conversational question answering, also the conversational context. And the prediction part actually predicts each word using its integrated context vector, the start, the end of the answer span. And the current state-of-the-art MRC model are based on BERT. We still use the lexicon input, but the other two embedding modules, such as the passage context embedding and the question context embedding, are performed by BERT using its built-in attention mechanisms. In particular, the passage context embedding achieved by self-attention, capturing words dependencies within context, and the question context embedding is achieved by inter-attention across the words in the question and the passage. And the output of the BERT is a sequence of integrated contextual vectors, which can be fed into a fine-tuned predictor to extract the answer span from the passage. And the MRC model can be easily extended to capture conversational context for conversational question answering tasks. For example, we can simply prepend conversational history to the current question or passage to convert conversational question answering to a singleton question answering. For BERT-based MRC model, we can simply prepend dialogue history to current question and use BERT to encode the conversation context in the same way as the question context. Although there are models that explicitly encode the dialogue history, such as the CLIQ-ai, their performance is inferior to BERT-based models. And actually, there's a trend in the research community to use a single neural network to replace all the dialogue modules, as I mentioned earlier. My team at MSR is developing a solid system to provide a solution to building task-oriented dialogue bots at scale using transfer learning, inspired by the pre-training and fine-tuning framework of natural language processing. First of all, we parameterize a convolutional QA system using an autoregressive model that subsumes different dialogue modules into a single neural model. But instead of using a vanilla neural language model, we pre-train a grounded text generation module, or GTG, that generates the response grounded in real-world knowledge for question answering. Then we can fine-tune the pre-trained GTG to new tasks using a system called the Conversational Learner, which provides a machine teaching interface for dialogue authors to interactively teach the bot by labeling the data. This slide shows how we formulate a modular dialogue system as an autoregressive model. The modular system can be viewed as a data generation pipeline, which consists of 4 modules: natural language understanding, dialogue state tracking, dialogue policy, and the natural language generation. If we implement each module use a transformer-based neural network and allow all these neural networks to share the same set of parameters, then the whole pipeline can be implemented using a transformer model, which we call GTG. Different from the, let's say, the GPT-2 model, this GTG actually plays different roles in the process of generating a response. We can use multitask learning to train GTG on large amounts of heterogeneous dialogue corpus. The first task is called brief state track, where the GTG takes dialogue history and produces the dialogue brief state. The second task is the grounded response generation, where the model takes input of dialogue history, combining dialogue history and the brief state generated by the first stage of the model, and combined with the database state and produce the natural language response. And the third task is an auxiliary task, which helps to ensure that the dialogue history, brief state, database state, and the response are all consistent with each other. Now, in summary, in this talk, I'll quickly review some of our recent work on developing a conversational question answering system. We show that conversational question answering system is a QA system with a conversational interface, and it's an instance of a task-oriented dialogue system. And we present many modular approaches to building these systems. We also quickly describe the new trend in the community, which we observe that people try to move from the modular architecture to a single model architecture, which we use a neural network model to subsume different dialogue modules. And this model can be trained on large amounts of dialogue data and fine-tuned to adapt to different downstream tasks. Yeah, thank you.
Thank you very much for your presentation. So we have around 5 minutes for the question period. So any questions from the audience? You can use the raise hand button to ask questions. So I can start with a quite general question. So most of the works that I've seen for using transformer architectures for modeling the dialogue history, I've seen that they're using the separator token to differentiate between the different dialogue turns. So, but my question is that what happens if we want to expand it to multi-turn dialogues? I mean that we have like multiple speakers at the same time. So in that case, what we need to do is we need to be able to understand that who was the speaker at each utterance. So has there been any work on that aspect in order to better have a way of representing the different turns by different speakers within a dialogue history?
It's a very good question there. We think about this, but our current system only handles, 2 players. One is the system, the other the user. When we have to deal with multiple users, there are different settings. For example, we assume that all the users are working together to solve one task, or there are multiple tasks. or multiple domains. So ideally, you need to have a hierarchical system, right? For the high-level system, we maintain the global state of the entire conversation, and at the lower level, you also need to track the behavior of each individual users. That's a very good question. I think we only have a system to deal with so-called multitask dialogue. The setting that one user want to achieve multiple tasks through one conversation. But what you suggest is a different setting. Yeah, but we still need a clarification, right? Multiple users, are they going to solve one task or also multiple related tasks? So.
Thank you. Questions from the audience?
Yeah, Jianfeng, hi.
Yeah.
I'm going to ask you a question. On this slide, you showed the parameter sharing, and you also showed in your ongoing project that you are trying to share a lot of parameters for different modules. So a general question is whether those parameters should be shared by different modules, or they should rely on different parameters. Have you thought about this?
We thought about it. Actually, when we first developed system like this, we always assume that for different modules, there's a separate neural network. But the problem is that these networks need to be trained using the module-based train data. It's very hard to collect, and then I think eventually we end up with the shared model because first of all, it will be much easier to collect all sorts of data, and you see that the data size is very unbalanced. We have a large amount of data end-to-end. Let's say we have the user input, system response. We have a lot of such data, but the label data is much less. For example, here we need some labeled, manually labeled dialog state tables. So the idea of the multitask learning is that if these are related tasks, then one task with less data can be helpful, can get help from related tasks with much more data. So I don't know exactly how it works, but when we run these experiments, all the results much better than training all these individual models using small amount of data. And most importantly, we believe that by doing so, we can leverage a pre-trained language model like GPT-2 or BERT, which has been trained on large amounts of web data. This is the capability of language understanding. This is so fundamental to all the tasks. It's like human, right? You have natural language understanding capability for all these tasks. So somehow it simulates how human learn the conversation. Human does not learn this, individual capabilities separately. He just take all. And internally, I think the modular system is, in some sense, designed by researchers to trying to simulate a human cognitive process. But what we are doing here is to make the boundary of these modules fuzzy. And it seems to work fine.
Yeah, I see your point. Maybe it is related to the amount of data that you have now. For example, you mentioned the GPT that works well for all those modules, but I can see that, GPT may be related to natural language understanding, natural language generation, but if you can see the dialogue state tracking, this is not a natural part of human understanding. This is some module that you implement to make the conversation. So I'm not sure that this part should use the same parameters.
Or you can view it differently. Let's say we have a large amount of S and R, right, from human-human conversation. And this B and the C are sort of additional labels by the user. So you can view the whole thing that we are using same amounts of large scale data, but now we add additional human supervisions to help the model learn not only how to generate the response, but also make the whole process more interpretable. You try to teach the system, so okay, probably you should generate the response, the brief state first. If you have the brief state as additional information together with the dialogue history, you can generate a better response. So I will view the whole process as a human knowledge enhanced machine learning.
Yeah, okay, I agree. Svitlana, you have a question?
Yeah, we have only maybe one question. We're already beyond the schedule, but yeah, if we can have one more question.
You're muted.
Yeah.
Oops.
Svitlana.
Thanks. I think you mentioned already in the previous answer that there is an amount of training data you need for training natural language understanding for this knowledge-based question answering. It depends on the database schema. So I was wondering to transfer this model to a different database, how much additional data do you need?
Okay, you're referring, I think.
So when you
in this way, right?
Yes, so to the sequence.
Yeah, this the model is a pre-trained model, and first of all, you can because for different tasks, the database schema is different. Right? It could be a free base, it could be a relational database. The data schemas are different. So one idea is to just collect all the data, and no matter what database schema is, then put it together. Because the data schema is in the input. The output is the formal language, so you can view the whole thing as an input to output mapping. Right? So for a particular database, usually you need to do a little bit of fine tuning if you have the task-specific data. It's very similar to pre-trained models for multiple natural language understanding tasks. For each particular task, you have small amounts of task labels. The task label here actually is the particular database schema plus the corresponding formal queries. And fortunately for this type of application, it's possible to generate a large amount of synthetic data, because the grammar is not like the natural language grammar. It's a database grammar. It's a very constrained. So you can generate a lot of artificial data if the real task labels are not large enough. Yeah, in reality you only need a very small amount of labeled task-specific data to adapt this model to your task.
Okay, thank you, Jianfeng.
Yeah, thank you.
We have to move to the third talk by Filipe Mesquita from Diffbot. And well, I will give a short introduction to Filipe. Filipe is a research manager at Diffbot, and he held a PhD from University of Alberta. And previously, he worked as vice president of data science at Mitra Media. And today, he's going to talk about the knowledge graph, which is built in Diffbot. So, Filipe, the floor is yours.
Thank you. I'm throwing my camera in for a second. I'll share my slides briefly. Just want to say that it's a pleasure to be here with you. I am currently in California, in the Bay Area, Silicon Valley, where Diffbot is located. And I do miss Canada a lot. I lived in Canada for 9 years in Alberta, and in a way, I feel very much so connected to Canada. So it's a pleasure to be here. Let me share my screen and be able to share my slides as well. I hope you can see my slides. And
yes.
Yes. Okay. So today I'd like to talk about the Diffbot knowledge graph, and try to make a connection with the main topic of this meetup, which is question answering. But let me start with Diffbot. So what is Diffbot? We are a startup here in the Silicon Valley, and our mission is to build a knowledge graph of the web. We want to have a knowledge graph that encompasses basically human knowledge, everything that we know collectively, to be in that knowledge graph. This is a research project as well as a commercial endeavor. We actually have customers using a knowledge graph, over 400 of them, and we are backed by investors that you may have heard of, at least the companies they have invested on. We are operating since 2012, but the knowledge graph was only released 2 years ago, 2018, and we are profitable, which is very rare for machine learning startups.
Filipe, do you want to put the full screen?
I prefer to leave it like this.
Okay, no problem. Okay.
Yes, I will actually have a lot of different demos. So the idea for this talk is to show you a lot of things, not to go deeper into any specific problem. It's a huge endeavor. Yeah, I want to show this with demos. But just, the basics, right? Well, what's a knowledge graph? Well, it's just a knowledge base that uses a graph structured data model, right? Where the nodes like represent entities like people or organizations. Like Diffbot will be a node. Mike Tung is the CEO of Diffbot. So they are both represented as a node. And the edges between them are the facts or statements, right? The fact that Mike Tung is the CEO of Diffbot, that's how you represent that knowledge in the graph. It's a very flexible way to represent the information. And you can use this in many different applications, right? You probably have used this on Google. When you search for something, you might have data as a result that comes from Google's knowledge graph. I think the biggest problem that Diffbot is trying to fix is that knowledge graphs are often limited by human curation. Most knowledge graphs that you heard about are probably heavily dependent on human curation. We hear a lot about Google Knowledge Graph, and we know that process is, and there is machine learning, but humans are very much so involved. So if you have humans involved on building a knowledge graph, you're always going to face these three main limitations. You're going to have limited coverage, the number of entities that you can cover, or the properties that you can cover, because basically everything has to go through a human. Limited freshness, right? The idea that you enter a fact or entity on a knowledge graph and you never revisit or revisit it not very often, it's a problem because the data itself becomes out of date. And also limited provenance. Most of the knowledge graphs that I know don't actually provide you with a pointer where they found that fact, which is quite important for several reasons, including trustworthiness of the knowledge graph. I think all of these three approaches can be solved with a fully automated knowledge graph, which you're going to present it today. But I do want to make a connection with question answering. There's a trend now on question answering research to see the text, right, the web itself, the documents on the web as a knowledge base. It seems like having a knowledge graph build from the text and then use a knowledge graph can be detrimental depending on the kind of questions you ask. But I want to give you some examples of queries that are much better to be answered with a knowledge graph than using like a reading comprehension model where you have one document, maybe few documents to be able to respond it. So one, and it's an opportunity as well for you to see knowledge graph, right? So one of the queries that I'm going to pose here is that the CEOs of software companies that are based in Montreal. So for this query, you would need to collect several different documents from the web. One, to figure out the people that are involved, that are the CEOs, then to figure out what are the companies that are involved, right? So in this case, you have this person, Paul, and his, the CEO of this company. So you have to get that information. That could be in several different documents, depending on each person. You also need to figure out this is a software company, which is another problem. You see, and thirdly, you have to figure out that currently it's true, that the data is not out of date, right? One document might be saying that he's the CEO, but maybe there is a newest document that says no, that there's a new CEO for this company. And this is one way to use our knowledge graph, which is a structured query. Like you can. This is the Diffbot query language. Is one way for you to get the data out of the knowledge graph. Other types of questions that are better to be answered with knowledge graph are those that require large-scale inference normalization, right? So such as most popular industries in Montreal. So you would have to find all the companies in Montreal, right? And then you have to classify them in certain industries, and then you have to count all of them. So this would be very hard to do on a reading comprehension model. And you see here, most of the companies are services companies and retailers, hospitality, software, etc. It's interesting, software is quite high on the list. So, I can also use the knowledge graph to help reading comprehension, right? Methods that use the text as a knowledge graph. So there are several different questions you can ask that it's hard to encode them in the knowledge graph, especially questions that start with a why or how. But you could actually use the knowledge graph to organize your text so that you can respond to those queries. One way is for you to annotate the documents, right? Here, two different queries. One is articles about Apple, the company. So we're using the Diffbot URI for Apple, the company, and you see that talk about AirPods, Apple apologizing, iOS, etc. This is all about Apple, the company. I made a similar query for Apple, the fruit, and you get a completely different result. Right, here's talking about Thanksgiving, different fruits, recipes, apple spirit, etc. So you can use this to retrieve documents that talk about the topic that you're asking about. But let me continue here. So the knowledge graph was launched again in 2018. It's fully automated, and it's based on actively crawling and extracting information from the web. Over 60 billion pages. We currently have 10 billion entities and over 1 trillion facts, and we keep adding a lot of facts every month. We actually create a new knowledge graph every 4 days from scratch, from the sources. And this takes us a lot of CPU cores and 2 data centers here in the Bay Area. The big I think takeaway I think from this presentation is to show you how a KG of this size can be built. There are basically 4 steps. The first one is when you look at a page, we try to classify what the type of the page is. What is the main topic of this page? Right? In the case of the Tim Cook page in the Apple website, the main type is a person. Right? We know because of visual cues, but also because of the text, the language model would tell you that this sounds like describing a person. The second part is to also determine the language. We work not only with English, but with many different languages. Right? So this page specifically is a product page in German. This is an event page in English, an article page in French, and this is a video page in Italian. And depending on the type of the page and the language, we would use a different extractor for that page. When you have the page, there are several different elements of the page that you can use to extract information, right? You can use the images, but to use computer vision, and you can get images and the color of those images for product, for example. You also have the values that are separated in the page. Like these are more traditional HTML, but we also use machine learning for this. Like we don't use rules to figure out that this is the title of the product. We would use machine learning to figure out that this is the title. So it works on any page, not only the domains that we have trained on. And then we have also natural language. I'll focus a little bit more on natural language content, right? But this is a demo that you can do yourself. You can go to Diffbot website and you can put any page here. Let's say you put a page of a product like this B&H photo product page. And the first thing that the API is going to do is figure out this is a product, and here are the things that I know, the fields that I know that are for product. The title, the text, the offer price, the specs, the images, etc. So this would be the first extraction, page classification extraction, right? Once we have extracted the values, we might have big contents or in natural language, and this goes to a different extractor, the natural language extractor. These demos also available on our website. So if you're interested and you want to test your own, examples, you can go directly there. So I've entered a description of a person here. This is something you would find on a person page, right? And the natural language extractor is looking for things like entities, like this is a person, and this person is mentioned with pronouns as well, so there's corrections resolution. And it's also looking for facts, so relationships between these entities. Right, the fact that Mike Tung is the CEO, these are automatically extracted here, so you can see all the effects. Mike Tung is the founder, is a CEO, is an employee of Diffbot, etc. We also extract qualifiers, so we know that Mike Tung is currently CEO of Diffbot because we have a qualifier that tells us so based on the text. This allows us to create complex relationships, not just binary ones. Of course, we do much more. We have this concept of open information extraction, where you can extract any property from the text independently, whether we have defined it or not. And we also allow our customers to define their custom properties on the fly. So this would be an example of a few shot classification problem. But this gives you an idea how we can analyze the text of the page to get more facts beyond what we can find on images and in data that's separated on the page as well. The last step is to get all of this data that comes from different places and creating one record for that entity. Right? I have several different pages on the web, and there's a lot of people with my name, right? So if I search for me, for my name on the knowledge graph, you're actually going to see there's over 60 people with my name. So we have to figure out that those people are not me, right? And we don't want their information in my profile. At the same time, I have several pages. So if I look at my profile here, I can show you that the information that we have here, like my name, the place I've been, my experience, pictures about me, my tweets, my top 3 publications. You can see that all of this information came from different places on the web. In fact, every fact has a URL where we found that fact, right? But the entirety of my entity comes from University of Alberta, Google+, LinkedIn, Google Scholar, ResearchGate, SlideShare, and Twitter. So record linking, figuring out which pages are about the same person or same organization or same product is quite important, as well as knowledge fusion, which is the problem of finding conflicting information, removing outdated information as well, and create a cohesive and correct record for this person. There's a lot of problems here that we could go deeper, but I just want to give you a quick demo of how this works. Like for me, if I call here my explain service, I can show you the similarities between the pages that talk about me. So it's pulling all the pages and create the similarities here. This might take a little bit of time. Let me continue. I can go back to it later. We have some ongoing research projects. One of them is called KnowledgeNet. And KnowledgeNet is a benchmark to create a knowledge base from text. And we've created this benchmark because we found that the current benchmarks that we had available to us were not ideal. They did not consider the entirety of the problem. You're often going to see benchmarks for different tasks like graph resolution, NER, relation extraction, anti-linking, but you're not going to find it. If you want to create an end-to-end system that tries to do everything together and try to reduce error propagation, you're going to have a hard time doing that. So we create a benchmark that can use both for training and evaluation of these end-to-end models. We can see that the baseline models, they're mostly the traditional pipeline approaches, are very far away from human performance. As we get more end-to-end models, then we are getting closer, but we're still not the same level as humans in this task. Other ongoing projects that we have at Diffbot are to combine computer vision, natural language, and structured prediction in one model, so that if you ask a question such as, "What color is this product?" right? That their answer could come from the image, or could come from the text, or could come from a table. And the idea that we have this information overlap allow you to do a better job than looking at each document individually, at which element of this page individually. Many other research problems, we don't do this alone, actually. We have several different collaborations. I don't know if I can show quickly one of the demos that we're working right now, which is to convert, I'll let it open, but it's to convert natural language queries into our DQL, or Diffbot query language, similar to the work that we just heard as well from Microsoft Research. So that users don't need to learn our query language. So as I said, we work with several different research groups, and we also have researchers in our team. But if you're interested in working on one of these problems, you can contact me. We do give free research access to the Diffbot KG, our tools, extraction tools, and in some cases we also provide grants if your research aligns with our goals. So I want to just wrap it up with some takeaways that we are working to solve automated knowledge graph construction. How can we remove human intervention from the process? And we want to do that at scale, at web scale. Businesses use our knowledge graph to get more information about people, organizations, articles, products, etc. We also provide tools and expertise for business to build their own knowledge graphs, and free access to researchers so that they can have access to a large-scale knowledge graph for their research as well. You don't need to do an internship on a big company to do that. You can have access directly today if you send me an email. And we are hiring. We have both machine learning researcher and engineer positions. today, so you can definitely take a look at the careers page at Diffbot. And again, thank you for your time, and I think we can have a couple questions.
Yes, thank you very much, Filipe. Questions? Yeah, see one hand.
Dr. Lapan, please go ahead.
Go ahead.
So thank you very much. I was just wondering, how do you gather with things that are contradict? Because with this thing of fake news, so good news is for some people and then fake news is for the others. So how can the machine decide?
Yes, so the process of knowledge fusion, which takes all facts that we found on the web and decide which ones we should keep as likely to be true. This is a machine learning problem, and the model has access to things like how likely is this fact to be true based on the extractor, right? If it's an image extractor, natural language extractor, or a table extractor or HTML extractor, but also the domain and the page. So that we can use some signals from the domain as well. So how likely is Wikipedia to be correct about a CEO of a company, as opposed to a random blog, right? So, or other domains on the web. So the model has access to that. It's definitely not a solved problem. And if you have too many people saying the same thing on the web, it's hard for the model to choose too many people saying the fake news, right? It can be hard for the model to choose the correct facts, for sure. So this is an area that we are actively looking for collaboration.
But you have a limited set of relation or type of entities that you're interested in. Say, for example, who won the last U.S. election? Then you would. There are some opinions about this. So how can the machine learning do something about that?
Right. So yes, we are interested in a select number of entity types, like people, organization, locations, products, and a set of properties as well. So the idea is that we are ever expanding that. I don't think we have who won the election. I think we do have who is the president of. So that fact is not yet established. Right? The transition hasn't happened yet. But if we did have who's the elect president of the U.S., then basically the model will be looking at based on our ground truth, how likely is this domain, let's say Fox News or what's the Smart News, right? Or this random blog to be correct when they call election, based on in the contradictions it has with other news that might have a higher likelihood of being correct, like I don't know, New York Times or so. It's if you think about this, we have a fraction of our knowledge graph which is maintained by humans, and that allows us to figure out this source more often than not contradicts with our ground truth, so we're gonna trust the source less. Does that make sense? So it's currently
data. It makes more sense. Thank you.
Yeah, thank you. It's metadata based.
Okay, thank you.
Yeah,
so we have a
Yes. Hello. Can you hear me well?
Yes.
Yes. So I'm Thomas Reed from Bombardier. I have a question, and first, thank you very much for this presentation. It's very interesting product, and my question is about one of the aspects that interest the Montreal NLP Consortium regarding ethics. In that area, I see obviously there's your web crawlers are going to catch a lot of personal information. So what is your approach regarding compliance to that data privacy regulation?
Right. Every information we get, our information is public, right? Paywall. So basically, anything that you would find with a search on Google, that's the idea. We do not store anything that would be that we think could be used for nefarious reasons. For example, we don't store email addresses of people, and other fields that might be used for nefarious reason. And we have a very strict process to onboard businesses to use our data. We're definitely looking for nefarious use of our data. We don't want give access to any company that might be using our data to spam people, for example.
Yeah, maybe if you just collect the information or collect the knowledge from public web pages, I don't think that you have a privacy issue there. But however, if you work with private data, then the issue will raise, right?
Yeah.
Good. Okay. Well, next question, Olivier.
Hello, can you hear me?
Yes.
Okay, great. First of all, many thanks for your presentations. It's a very big ambition to encapsulate the entire web in a knowledge graph. I have two questions. The first one is, how is your graph different from the one used by Google? And my other question was, how do you define, I mean, when you are building your graph, how do you define which element is, how can I say, is encoded as a node and which one is encoded as an edge in the graph? Is that something that you define manually from scratch, or that you define from scratch with some machine learning approach, or is it something more that you would, let's say, that would you build based on some other knowledge graph that could be seen as some sort of gold standard? How do you do that?
Right. So the first question is how our knowledge graph is different from Google's. So Google is based on Freebase, which used to be an open source project and was bought. A company that created Freebase was bought, and the project was basically internalized at Google. Google did not like other companies like Microsoft using it for their purposes. Now, every big company have their own knowledge graph. So the idea is that you have one knowledge graph that everybody can put data in and remove data from. So that is, in the Freebase years, were mostly people doing the collaborative kind of editing that we do in Wikipedia, right? So we would go add a new entity, add facts about this entity. They also had bots that would add information there, and a person could come and remove information that's wrong. Or and as I understand, and don't work for Google, don't speak for Google, but I understand they basically have scaled that process. More people, more bots, right? So it's basically, but people still have the final decision there. So it's an incremental knowledge graph, right? They keep adding into it. The second difference is that we are not incremental. We build a new knowledge graph from scratch every 4 days. So the idea is we are not making the decisions of whether this Facebook page and this LinkedIn page is for the same company. The machine learning model is doing that decision, and it's not perfect yet. And the technology is not there yet. But if we do improve the model by 10% today, I can commit that model, and in 4 days I have a knowledge graph that's 10% better than the one that was before. You're going to be hard pressed to think about how to do this if your knowledge graph is incremental. You can only add and remove edges or entities from it. So there'll be two main differences there in terms of the technology. The second question is, now, what are the pieces that we create automatically, or the pieces that we create as a human, and how to decide? So the schema of the knowledge graph we currently create with humans. So the schema will be what entity types, people, organizations, products. So we define that as humans. And what is the relationships that we can create between them, like CEO of. So the humans have defined what is the meaning of that property and what's the meaning of an entity type. Everything else is automatically. So populating all the people on the web, populating all the organizations on the web, all the relationship between organizations and people, that's automatically. That's done automatically with the extractors that are shown.
So,
Thanks.
So thank you very much again, Filipe.
Yeah,
And so we have reached the end of today's event. So before finishing, I would like to thanks everyone again for attending this event. Thank the speakers for the great presentation, and also thank Dr. Ni, who pretty much did the most of the hosting. So thank you very much again for that. So please stay tuned for the upcoming event, which is gonna be within a month, and the topic, we have already aligned a little bit towards that, and because the topic is going to be on knowledge graphs. So see you again in another month. Stay safe.
Yeah, thank you very much. Thanks to all the speakers again. So we can do a virtual claps. Thank you. Okay.
Have a good day and stay
Bye.
safe.
Thank you.
Bye-bye.
Thank you, everyone.